Welcome everybody to page 11 in the workbook. And this is the beginning of section 12.4. And this is a discussion about linear functions, otherwise known as planes. This is kind of one of the simplest types of surfaces that we can describe in three-dimensional space, and it's going to be a type of surface that we do a lot of work with over the course of the semester. Okay, so what we'd like to be able to do in this section is to be able to describe and recognize a plane, basically. We're going to talk about various ways of writing the equation of a plane and various properties that planes have. Okay, so let's get started here with a definition. Okay, so we say that a function is linear if it has a constant slope in each direction, and if it has that property, we're going to notice that it's a plane. It's a surface that's flat in three-dimensional space. So the key property is constant slope in each direction. Okay, let's illustrate that with a graphical example. So if you look at the picture down here below, I'd like to pick out a couple of points. So let's take a point P that's at the top of this portion of the plane that we're seeing. Okay, I'm going to choose two other points, Q and R. And maybe imagine that you're an ant on this surface starting from the point P. One thing that you could do, you could crawl along the surface towards Q along a straight line, or you could start from P and you could crawl along until you reach R. Okay, and here's the problem that I want to pose. Okay, so on which of those paths would your descent be the steepest? Okay, so you could either move from P to Q or from P to R. Which path would give you the steepest descent? Okay, I want you to think about that. Maybe even pause the video here at this point. Think about that for a couple of minutes and see if you can come up with an answer. Okay, welcome back. So, what do you think? Are we going to get a steeper descent from P to Q or from P to R? Okay, well, I'm not sure how you thought about it, but one way to think about it would be, notice that from P to Q, we're going, or between P and Q and P and R, we're going down the same distance. We're starting from the same point and we're ending up on the floor, okay, down here where Z is 0. And so because P to Q is a shorter path, it seems logical that we're going down steeper along that path. From P to R, we're going down the same amount, but it's taking us longer to do that. Okay, so we can make a couple of observations here. We'll maybe start with that one. Okay, so our descent is steeper along PQ than along PR. Okay, I'm just using the notation arrow to kind of represent that path that we're taking. Okay, another thing that we might notice is that if you choose a direction, okay, say you go from P to Q, does your slope change? Does the steepness change along that path? It really doesn't, because the surface is flat. It stays constant. And similarly, if you move from P to R, that descent, as we said, is not as steep, but if you keep on that path from P to R, your slope isn't going to change while you're on that path. Okay, so what we could say maybe is the following. The slope stays constant along each straight path. Okay, and the second property that we have here is an important property that describes any flat surface in three-dimensional space. If you choose a straight path and you walk along a plane, your slope is not going to change as long as you stay on that straight path. Okay, so we are ready then to write down our first formula for the equation of a linear function that is a plane. Okay, and this formula is going to involve slopes. Okay, so let's read this together. If a plane has a slope of m in the x direction and a slope of n in the y direction, and it passes through the point x0, y0, and z0, then its equation, it turns out, is given as follows. I'm just going to write it down here. z naught plus mx minus x naught plus n y minus y naught. That equation would represent the equation of this plane in three-dimensional space. Now I'm curious if that equation reminds you of anything that you might have seen before. Okay, what's kind of interesting about it is the fact that there are really two pieces of information that we have here. We've got slopes and we've got a point. You might remember something from calculus and algebra called the point-slope form for the equation of a line. I'm going to sneak that in up here. Y minus y naught equals m times x minus x naught. Okay, point-slope form for the equation of a line. If you take that equation and just rearrange it a little bit, you can add the y naught to both sides. And notice that when you do that, this equation looks very similar to the one that we have down here. So you can think of this equation that we wrote down for the plane as just being the three-dimensional analog of the point-slope form for the equation of a line. There are two slopes involved now because we're in 3 dimensions instead of 2 dimensions. Okay, and in the rest of the section, we will explore some problems where we go a little bit deeper into the idea of planes and use this formula that we just wrote down.